Hi geographers, welcome to this video about coastal management. In today's video we're going to be exploring some of the different approaches used to manage both erosion and flooding along our coastlines and think about some of the benefits and problems associated with the different approaches. It's probably worth us thinking about why the coastline needs protection. It's quite a good statistic at the top of the screen here that half of the world's population live within 60 kilometres of a coast and 3/4 of all large cities are at the coast. Now 60 kilometres might seem like quite a long way and certainly is going to be far enough inland to not be directly affected by some of the problems like erosion, but that means that those people are still probably very reliant on the economy and services and ecosystems that exist along the coastline. So we are very much connected to the coastline in many aspects of our lives. Also, the fact that our large cities, 3/4 of them are at the coastline, is also important in terms of where some of our most valuable property and infrastructure is associated with those cities. So if we think about the specific problems that the coastline faces, the first of those is coastal erosion. So we can see in this top image here how the retreat of that coastline through the erosion of those cliffs is threatening the community, the roads, railways, power stations, the houses, the businesses that are located along that coastline. And particularly where the value of that land is quite significant, such as where we do have houses, businesses, those things can be very significantly threatened by coastal erosion. The other problem is coastal flooding. So this occurs when we have storms at the coastline, often bringing with them storm surges, so very high waves and almost like a wall of water that's blown towards the coastline during strong storms. And as a result of rising sea levels, those storm surges are going to become more common and put those coastal regions at more risk in the future. So when we think about the different techniques we can use to manage the coastline, we're thinking about managing these two problems. Firstly, erosion, but also coastal flooding. A couple of key definitions to be aware of here. In this video, we're going to be mainly focusing on hard and soft engineering. So hard engineering looks at the use of man-made structures using resistant materials such as concrete or wood and metal to, and this is a really important word here, control natural processes. Hard engineering is very much about trying to battle against natural processes and prevent erosion and prevent flooding. We're also going to spend a bit of time looking at soft engineering approaches, and these are more natural materials or using natural systems in order to try and work with natural processes or work in conjunction with them. So trying to use what we know about how the coastal system works to reduce the severity or the scale of some of those problems of erosion and flooding. In a future video, we're going to look at these other two concepts here, but it's worth mentioning what they are as they relate to some of the things we're going to be looking at. Shoreline management plans are the formal documents that exist for each sediment cell, outlining exactly how a particular stretch of coastline is going to be managed. And integrated coastal zone management, also abbreviated to ICZM, is a very multidisciplinary way of thinking about managing our coastline. So all of the people and stakeholders that use and have an interest in the coastline are aware of each other's needs and are working sustainably and collaboratively to manage the coastal system with the benefit for everybody. Moving on then to think about some of these hard and soft engineering techniques. A good phrase to also be aware of in relation to these is that we refer to hard and soft engineering as being traditional approaches. These are the sorts of things that we have used for decades, if not hundreds of years in some places, to manage the risks of erosion and flooding. So we're going to examine now each of the hard and soft engineering strategies in turn. But before we do that, maybe just pause the video and see if you could name all of the strategies that you can see on this slide. Okay, let's go through each of these now then and think about how they work and some of the benefits and problems associated with each of the defences. So we can start with seawalls and revetments, and we can see an image on the left hand side of both of those things together. So we can see the seawall on the left hand side, okay, this structure here, and then we can see this sloping structure in front of it, which is known as a revetment. They work in slightly different ways. Seawalls aim to reflect wave energy back out to sea. So what will happen is perhaps as a wave approaches the seawall, the energy of that wave, because of the curved face of the seawall, will be thrown back out to sea, and the energy from this wave will hit the next wave that's coming in an attempt to try and sort of slow it down. It's obviously also acting as a physical barrier, raising the height of the coastline and providing a very, very strong, resistant barrier to the oncoming waves and erosion. Revetments perform a similar job. They don't reflect the wave energy back out to sea like a sea wall does, but as the waves are running up the slope, they are also going to be losing energy, and that is going to mean that by the time the wave reaches the top of the slope, it's going to have slowed down. As I said, both of them help to raise the height of the coastline, so they help to act as a physical barrier against flooding. The downside to them significantly is that they can cause the beach in front of the seawall to be scoured away, because as that energy is deflected back out to sea, it essentially creates quite a powerful backwash to the wave. So steps have to be taken to make sure that the beach in front of the seawall isn't lost through erosion. That's why in this image we've got this revetment at the foot of the seawall. It's helping to keep that seawall in place and mean that the beach material in front of the seawall isn't lost to erosion. One of the biggest benefits of seawalls is the amenity value that they have. So they provide a really important structure, maybe to act as a promenade for people to walk along, and other facilities like slipways or beach access in the form of steps can be built into them to enable people to still be able to access the beach. In terms of some statistics, they are very expensive, so we can be looking between £200,000 and £500,000 per 100 metres. And when you think about many sea walls being several kilometres in length, you can see how the cost really significantly adds up. On the other hand, they tend to have very long lifespans, quite easily 30 to 50 years or more. Those sea walls and revetments could last, provided they're properly maintained. Some examples locally in Dorset, Lyme Regis has two large sea walls running along either side of the town. West Bay has a sea wall, and so does the area around Bowleys Cove in Weymouth. So again, where we have valuable assets close to the shoreline, sea walls and revetments can provide a very durable, effective means of tackling erosion and flooding. However, that does come at a cost. Groins are another popular measure of hard engineering. We can see in the image here how those groins are built out to sea, what we would describe as being a cross-shore structure. So it's built at right angles to the shoreline, and the aim of them is to reduce longshore drift. They can either be built out of timber, but more commonly rock armour is now the more preferred method of building a groin, and that's because they require much less maintenance and they're less likely to therefore have gaps in them that would reduce their effectiveness. Groins on their own don't do a huge amount to stop erosion and flooding, so they're not going to do much to dissipate wave energy, but what they do is cause the beach material to get trapped between the groins and therefore make the beach bigger, and therefore it's the beach itself which is offering the protection to the coastline. So the groins are helping to build up the beach, and the beach is therefore then the barrier to erosion and flooding. Obviously with a bigger beach, we've got greater opportunity for recreation. We can see in this image, lots of tourists enjoying themselves on the beach. And that's going to be aided by the fact that that beach is much bigger because of the presence of the groins. We can see timber ones in the photo, but as I've mentioned already, rock groins have the advantages of being much more durable in the long term, and also have a bit more ability to absorb some wave energy because of the fact that those boulders stacked together have gaps between them where the wave energy can be dissipated. Often groins are used in conjunction with beach nourishment or beach recycling, which we're going to have a look at in a moment, and that's because the groins are used to then keep that new material that's been added to the beach in place. The problem with groins is that they can cause erosion to increase down drift, so areas further along the coastline in the direction of longshore drift. So if we imagine, for argument's sake, that longshore drift is moving in this direction, imagining this was the last groin. Past this point, erosion rates are going to increase, and that's known as the terminal groin effect. So groins only work up to the point of the last groin. After that, they can actually starve beaches further down the coast of an important input of material. Costs vary quite significantly, maybe £10,000 for a timber groin, upwards to maybe £100,000 if that groin is being made out of rock armour. Lifespan is relatively short for a timber groin, obviously almost indefinite for a rock groin. And locally in Dorset, a couple of good examples: Swanage. There are about 20 or so timber groins built along the beach in Swanage, and at West Bay they've used 2 rock armour groins to help trap material on the beaches there. Another method of hard engineering is the use of rock armour and also gabions. So rock armour is what we can see in this image on the left hand side. It's this pile of boulders that have been arranged, in this case almost as a bit of a revetment. We can kind of see a bit of a slope to them there. Where they're placed a little bit more haphazardly and randomly along the shoreline, then they're often referred to as riprap. But essentially they're performing the same function. The large boulders placed in front of the cliff help to dissipate the wave energy. When the wave crashes onto the boulder, all of the different little gaps between the boulders help to dissipate that wave energy. It gives a large surface area to absorb the impact of the waves. Again, they're very important where perhaps the land behind the rock armour is very valuable, and they're a good alternative to the use of sea walls. Gabions, on the other hand, are these cages that we can see, wire cubes, if you like, that are then filled with rocks, much smaller little rocks and pebbles, and they perform a similar job. So if a wave was to crash into there, the wave energy will be dissipated through all of those different stones that are inside the cages. The problem with gabions is that the baskets themselves, the wire cages, can start to rust even within 10 years or so because of the constant battering from the seawater. And the main disadvantage of rock armour is that geologically it doesn't blend in with the coastline. So very often we have to use a very different rock type to that which would be found naturally within an area, and therefore they can look quite out of place along a coastline because you have these huge boulders of a very different rock type piled in front of the cliffs. However, both of them are very effective at doing the job that they're designed to do, which is to absorb wave energy and also to raise the height of the coastline. In terms of their cost, we are not far off the same cost as a seawall, a little bit cheaper, maybe £100,000 to £300,000 per 100 metres. And in Dorset, some local examples include Lyme Regis and West Bay have both got extensive amounts of rock armour there. And in terms of gabions, Chesil Cove, is what that should say there, is a good example of where we have some gabions used to raise the height of Chesil Beach and to protect areas of Portland behind it from overtopping by the waves and from flooding. Final method of hard engineering is cliff stabilization. So we can see that going on. This is in Swanage, which is one of the examples of where this is used, but Lyme Regis is another place which has had very, very extensive cliff stabilization works. This involves anchoring the weaker rocks, maybe on the surface of a cliff, to the more solid bedrock below. Very often this can be done in a few different ways. It could be done by artificially smoothing the slope, so regrading the slope so it's not as steep. This is only going to be achievable if there is enough space at the top and bottom of the cliff. That wouldn't be appropriate in the example we can see here because we've got some buildings, a hotel and some houses built on top of the cliff. We can encourage the development of vegetation over the cliff. That can be done by putting netting across the cliff, which provides a structure for the roots of vegetation to anchor themselves to. And that's an important method of stabilizing the cliff face. And we can think about the drainage of groundwater out of the cliff. So you can see here some black pipes which will have been embedded into the cliff to help drain some of the water out, because that water adds a lot of weight to the cliff and increases the water pressure within inside the rock as well. The final method, which we can see by all of these little dots over the cliff face, you can see lots and lots of little dots here, which is where they have used anchors, sometimes known as piles or pins, to secure the weaker surface layers of rock to the harder layers of rock beneath. Obviously, this technique is very, very disruptive to any settlements or buildings that are on top of the cliff. In the case of Lyme Regis, people's gardens had to be completely ripped up so that machinery could access the ground to be able to drill the piles into the ground, and therefore is really only a kind of last resort if at all possible, because of the amount of disruption that it causes. However, it is very effective. It's hard to put a specific lifespan on these sorts of techniques, but certainly 50 to 100 years to secure that cliff face to the more stable rocks below. So moving on to think about soft engineering then, one of the options that we can consider is beach nourishment, or sometimes referred to as beach replenishment. So this involves replacing material or adding material to a beach that has perhaps been lost over time through erosion or through longshore drift. These sorts of schemes can vary quite significantly, maybe from just a few truckloads of material being driven and dumped onto the beach, as is the case in West Bay, up to much larger schemes like we can see here. This is in Pevensey Bay in Sussex, where sediment has been dredged offshore and that is being sprayed, what we call rainbowed, onto the beach, where it will then be moved around by bulldozers. This is a very expensive technique, and actually when you look at the upper end of the cost of it, isn't far off the cost of a sea wall. So I don't want you to for a moment to think that beach nourishment is a cheap method of managing the coastline, because it isn't. However, it's very good for beaches with quite high amenity value, where people want to maintain the character and the structure of the beach because it's an important asset for the town. Once that shingle has been or sand has been dumped onto the beach, it could be quite quickly redistributed by waves and currents and tides, so it does need topping up either throughout the year or quite regularly in order to make sure that the volume of the beach remains at the required level. This can be quite disruptive, however, particularly if the material is being delivered by trucks, because they're going to cause quite significant congestion on the roads. The beach might need to be closed while the material is moved around by bulldozers. Obviously that would be quite hazardous to members of the public using the beach. So that can have a negative impact and often needs to be done at the end of the winter, sort of before the tourist season gets going. So normally kind of in spring is when some of that replenishment work would take place. The replenishment material obviously needs to be as close as possible in terms of a match to the existing beach material, because you want that beach material to blend in. Otherwise it's going to, again, a bit like rock armour, look a little bit out of place and not blend in with the local geology. Limiting factor of beach nourishment and replenishment is the lifespan. It's relatively short. It may only be a year or so before that material has been carried away by longshore drift or has been lost through storms. A similar process is the use of beach recycling or beach reprofiling. So recycling involves moving sand and shingle from one area of accretion or build-up to an area of erosion. So this might be the case of just moving material from one end of a beach back to the other. So if longshore drift, for example, in this situation was moving material in that direction, what we could then do, drive some trucks to the far end of the beach, fill them up with sand and drive them back to this end of the beach and dump the material back there. Reprofiling, on the other hand, is what we can see going on in the image here with the bulldozer. It's about re-steepening the beach. Naturally, over time, the material from the top of the beach might be moved down through the backwash of waves, and the bulldozer can be used to move that material back up the beach. This is often done quite regularly, so in terms of a lifespan, a year or possibly less than that, in order to repair or to regrade that beach so that it maintains its function as a barrier to erosion and flooding. In terms of some examples, West Bay is a good example of where beach reprofiling happens. So on the east part of West Bay, there's a very, very steep bank known as East Beach. That is artificially steepened every year to make sure that it provides a significant barrier to the properties that are located behind it. The example that we can see in the photo is from Pevensey Bay in Sussex, where along with beach nourishment, recycling and reprofiling is used quite extensively to maintain the structure and integrity of the beach. Another good example of soft engineering is dune regeneration, and this involves planting vegetation in sand dunes to encourage that vegetation to grow, and as it grows it's going to trap sand and stabilise the dunes. This can often be done by transplanting seedlings of marram grass into eroded parts of the dune, and it will quickly allow those dunes to re-establish themselves and to grow bigger, and then the dunes act as a natural defence against erosion and flooding. This makes use of the processes which naturally form sand dunes. So in the development of sand dunes, the grasses help to reduce the wind speed and they help to hold the sand in place. So their roots grow down into the sand, they anchor it, and growing both vertically and horizontally, they help to make that yellow dune, that sand dune, larger. This does require quite intensive maintenance, and it might be that different areas of the dunes have to be fenced off to access to people in order to stop those seedlings being trampled. But it is a relatively cheap way of managing the coastlines. We look at the cost of only £200 to £2,000 per 100 metres. When we think about the cost of a sea wall is maybe £200,000 or more per 100 metres. The problem being that you can only use this where you naturally have sand dunes. You can't artificially create sand dunes where they don't naturally exist. So there are relatively few places where this is an appropriate means of managing the coastline. However, where dunes are present, such as in places like Studland, or in Sefton in Lancashire, or Dawlish Warren in Devon, those dunes act as a really important natural sea defence, and every step should be taken to make sure that those dunes are managed and enhanced so that they're as big and as sturdy and strong as possible. Final technique of soft engineering is managed retreat or managed realignment. This is not the same as a do-nothing approach, but this is where areas of the coastline are sacrificed in order to protect areas surrounding it. So what will happen very often is that new defences will be built further inland than the existing ones. So in this example we can see in the photo, this is Medmerry in Sussex, and normally this beach running along here would have been the natural defence to the land, farmland and properties and things behind the beach. This beach though was at risk of overtopping, and so what the Environment Agency have done is they built some new defences further inland, and we can actually kind of trace the rough outline of those defences. If we look here, okay, we can see the new kind of earthen embankments that were built. So they built those defences, and then they created deliberately this gap in the beach which allowed the seawater to flood into this area, creating a salt marsh essentially. And what this is now doing is acting as a kind of weak point along the coastline, so that any storm surges that might approach this part of the coastline, rather than them overtopping the beach further along here and maybe impacting this town, or further along here and impacting this town, the storm surge finds this weak point, okay, and essentially floods this area of marshland, which helps then to absorb the impact of the flooding and sacrifices that land in order to save the higher value land surrounding it. It's quite contentious because it does involve obviously land having to be sacrificed to the sea. Farmers will have lost this farmland, they would have had to been compensated for it. Any homes or businesses on that land will have had to been bought. But it is seen as being a very, very sustainable way of managing the coastline going forward. In terms of cost, it's very hard to put a value on this because of the value of the land. So it will vary from scheme to scheme in terms of how much it costs. The example here in Medmerry cost in the region of about £28 million. So it's not a cheap option. However, the lifespan, in theory, is much, much longer than trying to maintain the beach or to build seawalls, groins, rock armour, or other hard engineering techniques along that part of the coastline. Brings additional benefits as well in terms of the marshland. So salt marshes are a rare habitat, and the biodiversity that can therefore be improved as a result of creating that marsh, and also things like tourism and recreation. So as part of this scheme in Sussex, they've built footpaths around, cycle paths around the edge of the marsh. It's attracting wildlife enthusiasts, bird watchers to go and spot some of the rare species that are now inhabiting that marsh, and that has benefits for the local tourism industry as well. So this technique is about sacrificing one area of a coastline in order to protect higher value settlements surrounding it. So that concludes our little rundown of the main techniques of hard and soft engineering, those traditional approaches. We're going to look at more sustainable approaches like shoreline management plans and integrated coastal zone management in a future video. But a good practice question for you to try and bring all of this information together now would be to try and answer this question on the screen. So soft engineering should be seen as the preferred method for managing coastlines. To what extent do you agree with this viewpoint? So what you could do now is pause the video and maybe have a go at either planning or writing an answer to that question, trying to set out your opinion about the benefits of soft engineering, and also maybe some of the drawbacks of it in comparison to hard engineering. So in what situations would soft engineering be the most appropriate method for managing the coastline? But when might that not be the case, as a kind of counter argument to that viewpoint as well? So have a go at that, just trying to bring all of this information that we've covered together about hard and soft engineering.